Hey guys, Dave Mazzetta here to talk about distilling tiny embeddings models. This article and video are going to cover the BERT Hash Embeddings models along with a review of the BERT Hash model series. These models that were released today generate fixed dimensional vectors that can be used for semantic search, text similarity, text classification, clustering, and more. The BERT Hash models are a follow-up to our original BERT Hash series, which were built on Colbert and MUVERA, and this is a strong alternative to that. So we're going to cover everything related to the BERT Hash model series here and how it built up to releasing these models. First thing we'll go through is the original BERT Hash series of models. This is a Medium article called Training Tiny Language Models with Token Hashing. It's just a simple tweak to the original BERT model. So as you review this diagram, there's a hash tokens embeddings layer. The whole architecture here is taking the token embeddings, projecting it to a smaller size, and then back to the hidden size. Many have pointed out how Albert also did something similar, but this is even similar to that and simpler than that, and that is just projecting the token embeddings level, nothing more than that. So looking at the number of different ways, so let's say you want to build micro models, is something that I've wanted to do for quite a while. Back in 2023, I had dreamed of micro models, which I defined as less than 5 megs and less than 1 million parameters. So a couple of different ways you can do that, from changing the vocabulary size to the number of hidden dimensions to the number of heads or layers or a custom model architecture. With BERT Tiny, which is an original model released about a couple years ago, it's a 4 million parameter model, and 3.9 million of the parameters are allocated to the token embeddings. If you see in this calculation, you got 30K vocabulary times 128 hidden dimensions, and the vast majority of the parameters in this tiny model are donated or put towards the vocabulary. So the first step with BERT is running that embeddings matrix, and everything follows through that. One simple idea could be, hey, why don't I just change the vocabulary to 1,000 tokens? And that makes sense. Only 128,000 parameters now. The problem is now you have all these little tiny tokens, and your generated number of tokens for a document gets very, very long. So it actually increases processing time, because even though you only have 1,000 tokens, you're just generating a massive amount of tokens for when you're building text. So BERT Hash says, all right, well, maybe there's a way we can get the best of both worlds here. And you look at this token embeddings layer, instead of projecting to, straight from 30K to 128, why don't we add this intermediate projections layer that goes to a smaller size and back to a bigger size. So looking at this calculation, while it's not quite 128,000, you're looking at 30K times 16 times 16 times 128, which gives you about 490,000 parameters. So that's a much smaller number than 3.9 million. And surprisingly, small amount of code, as you guys see here, is all it takes to do this. It's really not much to it. Just adding this linear projection layer to do the projections in the hidden size. And everything else stays the same in the model. And so that this is what the BERT Hash series is, and this was the original. It was trained on Wikipedia from a copy from 2025, trained from scratch, and then also this model here talking about how small models benefit from being trained from scratch first, and then being fine-tuned or distilled on a downstream task. So this is what happened here as well. You're looking at these scores compared to BERT Tiny, which was 4.4, and BERT Hash Nano, which is the same number of parameters outside of the token embeddings layer, performs pretty competitively with BERT Tiny. One other surprising thing I found in this original BERT Hash series is that while the scores for BERT Hash models by themselves weren't particularly impressive, when paired with Colbert and later in action, you actually got some pretty competitive scores. And we'll kind of step into that next section, going back to the original article. So if I'm going to scroll down and show you the scores in this article and then go back into the embeddings layer. So looking at the Colbert MUVERA model scores, which are trained on BERT Hash, you're looking at scores that are pretty competitive overall, just using MUVERA alone, it doesn't look competitive when you're used to the state-of-the-art scores. But when you compare them to some other popular models such as All Mini LM, the difference is 0.03, which is a pretty small percentage for between 0.9 million parameters and 22.7. So you're looking at some pretty impressive scores just using BERT Hash. The problem with MUVERA is that it generates some very large vectors in order for it to work pretty well. And you see here, the main issue with MUVERA tends to need wide vectors to be effective. 5,000 dimensions, 10,000. And you can do things like quantization and such to try to shrink down the number of dimensions, and it works pretty well. But this article, now kind of covering all the background for BERT Hash, is actually going to show how just a straight, regular, dense embeddings model might actually be fairly competitive as well. So we're releasing 3 models as part of that: the 244K 50-dimensional dense in vectors model, the 448K, and the 970K. How are these models trained? And as you keep seeing me come back to this paper here, this well-read Students Learn Better on the Importance of Pre-Training Compact Models. I would say it's a very good paper to read. The link is right in here, and this article will be linked in the video. But the key concept of distillation is that we're going to transfer knowledge from a larger, smarter teacher to a smaller, less capable model. And this paper is talking about that. You can't just go from the downstream teacher model to a empty student model. It benefits from actually pre-training from scratch, and that's what all the BERT Hash models are. They're trained from the original same data that BERT itself was trained on, updated for 2025. Looking at what was done here, so kind of in the same vein as all these other models that are derived from BERT Hash, it takes the original pre-trained model and then runs this two-step distillation process. The first step distills embeddings from a larger model, a 22 million parameter model, and then it'll go through a second step where it actually distills it again using a cross encoder. And I tried a lot of different models, as you can see here. There's all sorts of models that I tried, from just the very popular All Mini LM, which is very similar to the mixed bread X small. That's just a fine-tuned version of All Mini LM. You got the large version of mixed bread, you got Granite, you got Embeddings Gemma, you got the popular Quen 600 million parameter model, and so forth. And one thing that I discovered was that it seemed like when the models were more complex, that these small models, even when you distill the embeddings, it just couldn't quite learn from them as good as a model that's closer in its size. And the same was true for distilling from cross-encoder scores. The larger cross-encoder scores, it just couldn't learn from them as well as the smaller ones. And, theory I have is that these models don't have the capability to learn these, the nuances of the data, so that the best thing to do is to find a model that's capable but not vastly larger. And you could even look at, I think someone termed it online, of progressive distillation or sequential distillation or chain distillation, whatever you want to call it. But the idea of being, instead of going from a model that's 600 million parameters all the way down to 960K, 970K, you would sequentially go from 600 to 100, 100 to 10, 10 to 970. And I haven't tried that as part of this, but I think that's a good future task to investigate, because I do think that you actually could probably get even better scores than what I'm showing here if you took an approach like that. So let's look at the evaluation of how these BERT Hash embeddings models, remember, they're single layer, pooled mean pooling. There's no colbert, there's no nothing. It's just going from text to a single vector. So looking at the scores for MUVERA, which all of these these models down here are the original BERT Hash series of MUVERA released. And remember, once again, MUVERA takes these multi-vector colbert vectors and squishes them down to a single layer, but you need to kind of make them quite wide in order for it to properly remember enough information from the Colbert model. So looking at these scores, you see that for the smaller model, the 0.2 million parameter 200K, the MUVERA model is better across all of these scores for the most part, but it's still within relative range. And then for 400K, it's a lot closer. You're really only off by a little bit. And then surprisingly, for the 970K model, the BERT Hash Nano Embeddings, across the board, the scores are higher, by a significant margin. So let's see, the original MUVERA paper, suggests that you should pair the MUVERA single level dense embeddings with, a re-ranking pipeline, which would be the Colbert pipeline for the top 100 results. So let's kind of tweak that and say, okay, we're going to compare, MUVERA with a re-ranker, but also these embeddings models that have just been created with a re-ranker, and see how the scores for those look. So for the 200,000 parameter model, you got, it actually closes the gap quite a lot. I mean, the average is really only a little bit off for the 200K parameter model, and for the same for the Pico or the 400K parameter model. It's just, about the same gap. And then for, once again, as before, the 970K, actually pairing a Colbert re-ranker with this BERT Hash Nano Embeddings model yields better scores. So let's, compare now, once again, looking, full-on re-rank of these data sets with a full vector, multi-vector maxim, which is slow, and then some popular embeddings models. I'm taking All-Mini LM, and then the one that was fine-tuned or distilled on, which is a similar version to All-Mini LM. So we're looking at 22 million parameter models versus, micro nano models that are less than 1 million parameters. So if you compare, Colbert MUVERA Nano by itself with the the full vector maxim, it's only 3673 versus 3927, and then once again, this 3673 is the full on, just re-ranking everything, not even using a intermediate dense embeddings layer, which, if you're only working with 100 records, that's fine. But the idea is that you have some sort of repository of information. You're dealing with, millions of documents, or hundreds of documents, or thousands of documents, where it wouldn't be practical to put all of those into a single re-ranking request. So looking at the difference between the full vector maxim and, re-ranking the top 100 using BERT Hash Nano Embeddings, you're really not too far off. Only, it's attaining about 98% of the performance. And then, compared to 95% for the MUVERA version, the big difference here is you're looking at the 10K dimensional vectors versus 128 dimensional vectors. So if we just take 10,000 sample vectors at float 32 and compare the disk space needed, you're talking about 400 megs versus 5 megs. So quite substantial disk space usage. And at the nano level, it actually has better scores. But even for Pico and Femto, it's not too far off if you wanted to trade off even more accuracy for speed, performance, and disk space. So, these models are all something that you can easily swap in. If you're using TextAI or any embeddings method, census transformer is fully supported. Keeping in mind these are custom models. It takes custom code, so you have to set the trust custom code flag to true. But otherwise, you can run a sentence transformers encoding on using any of these models, whether it's MUVERA or the BERT Hash embedding series, and then compare, re-rank it using a Colbert pipeline. So wrapping this all up, this introduced the BERT Hash embedding series of models, and they pack quite a punch for being less than 1 million parameters. You have to keep in mind, very few, if anyone's really looking at models at this range. Most people are, happy with a 1 billion parameter model being considered a small model in this day of the LLM. I'm talking about, 900K, 400K, 200K, things that very few people are really looking at. And you ask, why would you even want this? What's the benefit? Where is this going? For on-device semantic search, or on-device similarity comparison, on-device RAG, you're talking about models that could be really run on very low resource devices. Certainly mobile phones, but you're getting in the range, especially in the femto layer, you get in the range that you could run it on a fairly powerful microcontroller. So there's a lot of different, use cases. Certainly the whole mobile on-device privacy component, I think, is a big one. But the fact of the matter of being able to just run, even for let's say that, the Nano series, you're comfortable with the accuracy level here. There's nothing to say you could just run, and save yourself some money on inference costs and run on very tiny VMs and not have to have some big giant GPU machine to build encoding. So that's also another option. Smaller isn't just edge. It also could be just you're reducing your usage of how much you need to spend on vectorization. Another big takeaway from this task, which I think leads into some future work and future investigation, is that I found that if you want to distill models, you can't just go from 10 billion down to 100K. You need to have some intermediate levels, and I think that some of the outcomes out of that could be a really strong 20 or 30 million parameter model when you distill it down, and then that model could train a really, really strong million or 500,000 parameter model. So a lot of different aspects of things that could be investigated here. This article is all online. The link is going to be at the end of the video, and there's all sorts of links to the papers and other areas of investigation. But if you're in the on-device, looking for a model to help you with on-device semantic search, you're looking for something to help you save with inference cost and more, definitely take a look at this model. It adds a lot of value, I think, and it's something that you can, certainly investigate further as you go along. Hopefully you found this helpful. Have a great day.